Hey guys, in this post we'll be exploring how well two key offensive stats, third down conversion rate and total yards gained, can predict whether the Baltimore Ravens won a game. We'll use logistic regression, a standard statistical technique for binary outcomes, to model the probability of a win. Data we'll be using is the 2018 to 2024 seasons of the Baltimore Ravens, which was taken from ProFootballReference.com. I aggregated all 7 seasons into one file, which I'll be using for other statistical analyses. Since we're only using a few features, there's no point in us using the full dataset with dozens of columns when we only need a fraction of them. So what we're going to do is extract the columns: season, date, week, opponent, total yards, third down made, third down attempted, and result. All of these will be placed into a separate spreadsheet so we can focus on the features relevant for this analysis. Along with that, we'll do some feature engineering where we create 2 more columns: win binary and third down percentage, which will also be included in our analysis. Win binary will serve as a simplified column for the computer to read wins as 1 and losses as 0. Third down percentage can simply be calculated by dividing the third downs made by the third downs attempted. Every time I try to import only using the file's name, it doesn't work, so I prefer to load the file in using a path link, which includes the folders the file sits in. You can do this by right-clicking the file in whatever folder it's in, clicking copy as path, then pasting it in the parentheses. Make sure to include an R just before the full quote of the file path. This is needed because Python recognizes backslashes as a particular command and will thus misread the file path. The R tells it they are a part of the file. This is the full code of the logistic regression that we're implementing. As always, we're going to start with importing the pandas library, the staple for data manipulation. Next, we import NumPy, which is used for advanced math calculations. Anytime you see NP in the code, that's NumPy being called. The next NumPy line uses a linalg submodule for linear algebra and also imports inv for the matrix inverse function. This will be used in the Newton-Raphson Iterations. Next, we import matplotlib, which is a standard library for visualizations. In the last section of the code, we'll see lots of PLT, which is the command for the visualizations or the graphs that we'll be doing. Seaborn is a simplified subset of matplotlib that's specialized for custom graphs. SNS is a shorthand command. Stats Models API is a main library that will be used for logistic regression. And lastly, we're importing 2 special visualizations from the scikit-learn library, Confusion Matrix and Calibration Curve. We load in our 7-season spreadsheet file. We're using a CSV format instead of XLSX since CSVs load much faster, even though they take up more space. DF stands for data frame, which is Panda's own form of spreadsheet that it will hold our dataset in. DF is just a common sense variable name we're using, but it could be whatever you want it to be. Anytime you see DF in this script, that means we're calling our dataset. We use the X variable to declare our selected quantitative predictors, third down percentage and total yards. DEF calls for our dataset that has these features, and of course the brackets contains them into a subset to ensure those are the only features that are focused on. These are our independent variables. In the next line, we use the SM alias, which calls for the Stat Models API library that we imported. We follow that with add constant X. This assigns a column of 1s into the subset we just made so the model can learn an intercept term, which is a baseline prediction if all other variables are at 0. If we did not do this, the model would assume the probability of winning is 0.5 even if both of those features are 0, which is unrealistic. You are absolutely not winning a game with 0 total yards, and you're super unlikely to win with 0 third down conversions. Then we declare our response vector, which is win binary. The model will recognize wins as 1 and losses as 0. This is vital for logistic regression since we're working with binary either-or outcomes. This is the actual initialization of logistic regression. Everything after this will be tuning the model. We'll use common sense to call this variable model. Again, we use SM to call for the Stats Models API module, and we access the logic class inside of it, which is literally logistic regression. We set the argument y and x for our binary response vector and our design matrix with our predictors that we just went over. The model was currently unfitted, so we then follow with the fit method, which applies maximum likelihood estimation, or MLE, to find the optimal coefficients, intercept, and slopes that maximize the probability of observing the given outcomes. Again, MLE maximizes the likelihood function, but in this case, we're using negative log likelihood since this model is using the Newton-Raphson optimization algorithm, which minimizes the functions. The method also displays the current function value, which is the negative log likelihood at the final iteration, which is called convergence. Convergence is simply when the optimization algorithm has reached a point where updates to the coefficient are so small there's no noticeable difference in the negative log likelihood. This will output the results of the model's implementation. In the same way we selected our two features a few lines back, this line does the same, except it's creating a new feature since predicted probability is not already in it. On the right side of this line, we call our model variable and use a predict method with it, which will return the predicted probabilities, which is the primary result we're looking for. We want to see the probability of a win given our selected features. This line is set up to establish that output for us when the analysis is done. And lastly, we use x as an argument since that is a variable that contains our two selected features, third down percentage and total yards. We're creating a new column called predicted bin that will hold the results of the predicted probabilities as they're categorized into various intervals. We assign that to a pandas method called cut, which converts continuous numerical data into discrete categories. Its argument will be predicted probability. Since probability is by default continuous, ranging from 0 to 1, we are binning it into intervals 0.1, 0.2, and etc. The second argument uses a numpy array of those intervals, which are the bin's edges. 0 is where the bin will start. 1.1 is where it will go up to, but not include. So it'll actually stop at 1.0. And 0.1 is the increment it will go up each time. So it'll go 0.1, 0.2, 0.3, and so on. Though not specified in the code, the arrange method by default is a half-open arrange, meaning the argument does not include the edges as we just went over. This helps avoid overlapping intervals in the case where if we have bins 0.0 to 0.1 and 0.1 to 0.2, then where will 0.1 go? We'll name this variable calibration, which will observe how well the predicted probabilities are aligned with the actual outcomes. The group by method will point this function to our full data frame along with the predicted bin column we just created. And it groups each row by bin label, from 0 to 10%, 10 to 20%, all the way to 90 to 100%. Each bin will have two calculated values. The first will be actual win rate, which will contain the win binary and the mean proportion of those wins. Meaning if 7 out of 10 games were wins, that's a 70% win rate for that particular bin. Then there's average predicted, which tells you what the model thought the average win probability was for that group. The features predicted probability and, again, the mean will be used in this bin. Lastly, the reset index will convert the group result back into a flat data frame with predicted bin as a regular column. Remember, we had to create that column, so making it a regular column and not an addition will make for better plotting. Lastly, we're going to print the results of the first games, which we'll be using in our math breakdown later. This next section of the code will track the Newton-Raphson iterations that will illustrate the learning part of machine learning. What we'll be seeing is how the coefficients update with each iteration until they're as accurate as possible. I will not be doing a line-by-line analysis of this section as it isn't necessary for the model to run. I only included it to illustrate how the algorithm works through the iterations. I'll break this down more in the math section. Now for the math breakdown. Our goal is to measure the probability of the Ravens getting a win based on the third down conversion rate and total yards in a game. The outcome of a game is binary, either a win or a loss. Since it's binary, we are classifying wins as 1 and losses as 0. We have our two predictive variables, x1, third down conversion percentage, and x2, total offensive yards gained. And our response variable is yi. Y, the outcome, a win or loss, and I, the given gain that's being evaluated. Logistic regression models the probability of a win as p of y equals 1, conditional x1 and x2, meaning what is the probability the Ravens will win a game given the conditions of the third down conversion rate and the total yards gained. This probability is determined by three coefficients: beta naught or beta 0, which is the intercept, the baseline log odds when the predictor's values are 0, beta 1, which is the effect of third down conversion percentage on the log odds, and beta 2, which is also the effect of total yards on log odds. Together, these form the linear combination z equals beta naught plus beta 1 and conditional 1, which is the third down percentage, plus beta 2 and condition 2, which is the total yards. The z value represents the log odds of winning. Log odds are the raw scores that the logistic regression model was calculating. It's the dough before the bread. On the surface, the numbers displayed by log odds have little meaning, but just know that they're necessary for determining the probability as precisely as possible. We will later transform the log odds into a readable probability, which is good old percentages, using the sigmoid function. Once we've defined our models of variables, the first actual calculation the logistic regression makes is the linear combination of predictors like we just went over. We just went over Z, which is the raw log odds, the uninterpretable version of the probability. The X variables remain their assigned values, and the coefficient variables, or the B's, are the coefficients of the X variables. A coefficient, also called weights, is the variable's effect on the log odds of winning. We're essentially weighing each variable by how much it impacts the outcome of a game, particularly on the logarithmic odds scale. The coefficients are calculated from the MLE application to the dataset, which includes all games. It tries to match the predicted probabilities to the actual wins and losses, testing its effectiveness. Of course, it's not perfect, but it gets as close as possible, hence probability. One thing that took me a long time to finally realize is that these coefficients are not calculated in a conventional algebraic form. It's not that we have a cookie cutter equation where we plug the values into the variables and simply solve. It doesn't work out in that way, in this case. These coefficients are results from an iterative algorithm called Newton-Raphson. Once we have the coefficient results, we plug them into the linear combination equation, then put that through the sigmoid function, and the result of that gives us both the predicted probability with the actual outcome of each game. Now that we have our log odds scores, the Z, for each game, we need to transform them into something more useful, probabilities between 0 and 1. This is where the sigmoid function comes in. The sigmoid takes any real number and squashes it into a range between 0 and 1. It's defined as sigma of z equals 1 divided by 1 plus Euler's e to the power of negative z. Sigma of z means take the number z, make it negative, then raise Euler's number e to that power. Add 1 to this result, then divide 1 by the total. The output is a number between 0 and 1, which represents the predicted probability of a Ravens win. A log odds of 0 is a 50% chance of winning. A positive log odds, where z is greater than 0, is greater than 50%, and a negative z less than 0 is less than 50%. Going off of that principle alone can give us an idea of the chance, but we want to get more precise. Otherwise, that's no difference from saying the Ravens are more or less likely to win. Let's apply the log odds from the first 3 games to the sigmoid function and see if the resulting predicted probability matches the one in the output. Euler's number is 2.718281 and infinitely continues, but we'll stick with 6 decimal places. We set that to the power of our log odds 0.754583, whose result is 0.470206, which will round to 0.702. That was the hard part. Now we plug that into the sigmoid function. 1 divided by 1 plus 0.4702 equals 1 divided by 1.4702, which equals 0.680179, which is just about the same as the computer's calculation of 0.680176. That only happens since different calculators have their own rounding errors. Regardless, both numbers round to 68%. So now that we've used the sigmoid function to get our predicted probabilities, how do we know if our model's predictions are any good? The linear combo gave us the log odds. We put the log odds into the sigmoid, then take the result of the sigmoid, which is the predicted probability, and now we're going to put that through the likelihood function. With the likelihood function, we're measuring how likely the model, with its predictions, will match to the actual game outcomes. All we're doing is taking the predicted probability of each game. If the game was a win, the probability stays. If the game was a loss, we subtract that probability from 1. For example, Game 2's probability was 0.7442. So since that game was a loss, we subtract that 1 minus 0.7442, which results in 0.2558. We calculate the likelihood of observing all the real outcomes using the predicted probabilities. The L is the likelihood function, which multiplies the chance of every outcome. The product symbol is the product notation, which multiplies terms for all the games I equals 1 to n. We take the likelihood terms of each game, multiply them, and the product will be our final likelihood function, which leads to our next issue. Once we multiply all those likelihood terms, which are small decimals, our resulting number will be a very small decimal, only a few steps away from 0. Something like 0.0000841, which isn't interpretable. This is where log likelihood comes in. This converts the likelihood function into a real number that we can do something with. We're not going to get into the deep math of log since it gets messy. We just need to understand its function. Log is basically the opposite of an exponent. It must be noted that we're using natural log, not base 10 log. Most calculators' log symbol uses base 10. Make sure you're using natural log, symbol shown as ln, before you make that calculation. So yup, we just take the log likelihood of each game, add them all together, then our sum is our total log likelihood. Now that we have the total log likelihood, which is negative 64.881, what do we do with it? We test the significance against our log likelihood of the null model, which is negative 73.365. We do this by calculating the pseudo r-squared formula, which will be the quotient of the log likelihood divided by the log likelihood null subtracted from 1. The quotient is 0.8844, which subtracted from 1 equals 0.1156. The ultimate answer is that our model improves log likelihood by 11.56% compared to the null model. This means our application of two variables to predict the win is somewhat impactful, but of course not a lot. As a rule of thumb in McFadden's R-square, 0.2 to 0.4 is the ideal range for a well-fitting model. Below 0.1 is a weak fit, which isn't much different from guessing, and over 0.4 is too confident, which usually means an error was made in the analysis. So our 0.1156 is, admittedly, a little underwhelming. For each of the three coefficients, we first compute the residual, which is the win binary 1 or 0, minus the predicted win probability, then multiply the residual by the respective feature's value. Let's say game 1 had a third down percentage of 0.45, total yards of 340, it was a win, which denotes a 1, and the predicted probability was 0.7003. The residual is the win binary minus the predicted probability, yi minus pi I. So 1 minus 0.7003, which equals our residual of 0.2997. If the game's outcome was a loss, it'd be 0 minus 0.7003. This is what we are doing for all games. Once we have all the game's residuals, we then take them and, in separate equations, multiply them by each feature. So for the first intercept, we multiply every residual by a simple 1, which is 1 times 0.2997 for game 1. For the third down percentage, we multiply each residual by the respective game's value for that, which was 0.45 for game 1. So that'd be by 0.45 times 0.2997 for just game 1. And we do the same for total yards, which was 340 for game 1, making 340 times 0.2997. With each feature as its own equation, we do these calculations for all games and simply add them all together. The resulting answer, our gradient vector, will be a matrix with the three sums stacked on top of each other. The Hessian tells us how fast the gradient is changing with respect to the coefficients. In other words, while the gradient points us in the right direction, the Hessian tells us how steep or flat the surface is so we can adjust our step size. In doing this, we build a weight matrix, W. Each element of W is a game's predicted probability multiplied by its complement, the complement simply being the predicted prob subtracted from 1. So since game 1's predicted prob was 0.7003, its complement is 0.2997, which, when multiplied, equals 0.2099, the weight of game 1. We put game 1's weight against a matrix of the features which are multiplied within each other. This is the matrix for game 1. We do this for all games, add all their matrices, and the result will be a final matrix of the same size, but it'll contain the sums of all the games. All of this happens under the table, so we won't be seeing that final matrix. The whole math process we just did is recalculated with each iteration. We are iterating or updating the coefficients to be more accurate, a loop of sorts. The first iteration treats all three coefficients as 0, 0, 0 as a baseline. This means the model has no prior knowledge of previous game data, which means the probability can't be anything more than a wild guess, which is 50%. They may win, they may not. This makes the model blatantly wrong. In the first iteration, we take the gradient and compare it to predicted probability, which is 0.5 for everything right now, with the actual outcomes for each game. The residuals are large since the model was ignorant. Then we calculate the Hessian, which measures how confident the model was in its predictions. Once those two derivatives are computed, the algorithm updates the coefficients to be more accurate. These iterations happen repeatedly until the updates don't change anymore, meaning it's gotten as accurate as possible, which is convergence. All of this is happening under the hood. There's nothing in the output of results that shows how much the updates have changed. We only know it did its job because of the converge showing true. Yet I included a section where we track the iterations so we can see them update in real time. Again, in the first iteration, the model starts all the coefficients blindly at 0. The updated coefficients after the first iteration is negative 2.39 by 4.13 by 3.36. After the second iteration, it goes to negative 3.22 by 5.32 by 4.56. There were a total of 5 iterations, so in the last one, which we have in our final output, negative 3.33 by 5.47 by 4.73. We're not going to get too deep into the math for this part. Beta naught, the intercept, decreased from negative 2.39 in the first iteration to negative 3.33 in the final iteration. This shift downward helped balance the upward movement of the other two coefficients. Since the intercept reflects the baseline log odds of winning when both predictors are 0, this drop means the model adjusted its baseline downward to compensate for the increasing influence of the actual predictors. It ensures that the predicted probabilities still stay within a realistic range between 0 and 1 as the model becomes more confident in the features. Beta 1, the third down percentage, increased significantly, jumping from 4.13 in the first iteration to 5.47 in the final iteration, which shows that it's a strong predictor of winning. Beta 2, total yards, had a lesser but still decent increase from 3.35 to 4.72, showing that it's a moderate predictor of winning. This is what outputs in the terminal after running the script. First, dependent variable, win binary. We're predicting if two variables, third down conversions and total yards in this case, predicts wins or losses, which is a pair of binary outcomes. 1 means wins and 0 means loss. Next is the model, which is logic, which is shorthand for logistic regression, just shows the name. Next is the method that we use, which was maximum likelihood estimation. Next is the date and time when this analysis was executed. Next is converged. The algorithm successfully found a set of coefficient values that maximize the log likelihood function. This means the model is stable, hence why it says true. If it was false, that means the model is unstable, which could be due to a number of factors. The covariance type. This measures how well the standard errors were calculated. Non-robust is the default value, meaning the model was correctly specified and errors meet all assumptions. Number of observations, the amount of observations in our data set. The games we're taking data from, which is 116 since we're doing the last 7 seasons. Degrees of freedom, or DF residuals. This value is the number of observations, 116 games, minus the number of predictors, 2 as shown in DF model, minus an extra 1 to account for the intercept. This is not to say we're deleting 3 games. It's that the predictors take away from the flexibility of the data set. A rule of thumb for the DF residual is you generally want it to be at least 50, ideally greater than 100. Less than 50 is dangerously unstable, and over 100 is very stable, thus more accurate. And the DF model is a number of predictors used in the model, which we're only using third down percentage and total yards, which is only 2 predictors.
On to the fit quality, starting with pseudo R-square. Logistic regression does not use squared errors like linear regression does, so we use a pseudo R-square to illustrate how well the model performs relative to a null model. We use McFadden's R-square in this case. Its interpretive value should generally hover around 0.20, ideally higher than 0.30. Less than 0.20 indicates weak explanatory power, and above 0.30 means a strong fit. Though a strong fit is not typical for logistic regression since it deals with binary outcomes. Our model's pseudo R-square is 0.1156, which is actually typical since we're dealing with binary outcomes, especially since we're only using 2 predictors. Log likelihood. It works by assigning probabilities to each game outcome based on the current model's predictions. If a game was a win and the model predicted a high probability of a win, it's rewarded. If it predicted the opposite, it's penalized. This score is based on multiplying the probabilities across all games, then taking the log so it doesn't underflow. The higher, less negative this value, the better your model fits. In our case, the log likelihood is negative 64.881, which is the value our model achieved after the optimizer, the Newton-Raphson, climbed the likelihood hill and settled at the best coefficients. Log likelihood null. This is the log likelihood of a dumb model, one that only uses an intercept and ignores all predictors. It's like saying, let's just always guess the average win rate no matter the third down percentage or yards. This is the baseline score. Ours is negative 73.365, which is worse than our model's log likelihood, negative 48.016. That's what we want. It means our predictors actually improve things. Likelihood ratio test p-value. It takes the difference between our full model and the null model and asks, is this improvement statistically significant, or could it just be random chance? Then it compares that to a chi-square distribution with degrees of freedom equal to the number of predictors. In our case, the likelihood ratio test p-value is 0.0002068, which means there's strong evidence that our model is better than guessing the average win rate. This tells us that our predictors matter. Coefficient. These are the final coefficients we found through the maximum likelihood estimation. Each one tells us how much its variable influences the log odds of winning, not the raw probability. The intercept, negative 3.3348, is the baseline log odds when all other variables are 0. Third down percentage, 5.4730, is strongly positive. Higher conversion rates dramatically increase win odds. Total yards, 0.0047, is a much smaller effect. It adds a bit to the log odds, but not much. Standard error. This is how uncertain we are about each coefficient. It's based on the curvature of the log likelihood peak, aka the Hessian. A smaller standard error means we're more confident in that coefficient, z. This is the test statistic. Each coefficient divided by a standard error tells us how many standard deviations away from 0 each coefficient is. The bigger the z, the stronger the evidence that the predictor has an effect. P greater than z. This is the p-value for each coefficient. It tells us if this predictor had no real effect, meaning the coefficient is 0, what's the chance we get a z-score this extreme just by luck? A p-value less than 0.05 usually means we consider it statistically significant. Finally, we have the quartiles, 0.025 and 0.975. This is the 95% confidence interval for each coefficient. It gives us a range where we believe the true coefficient is likely to fall.
Now that we have completed the analysis, we want to see what the results actually mean. As of now, all we have is that ugly terminal output that shows a bunch of terms and numbers. For logistic regression, we're going to be using 7 types of graphs to illustrate our results. We'll kick us off with a scatter plot, one of the more common graphs. This is more exploratory, gives us an overview of the data without having to stare at numbers. This visual shows the relationship between our two predictors and how much they overlap. Orange dots are wins and blue dots are losses. The x-axis is third down conversions and the y-axis is total yards. We see the data points are scattered pretty widely. Generally, we should be seeing the wins tend towards the upper right corner and losses toward the bottom left. Common sense can tell us that a game with a low amount of total yards is more likely to be a loss. The league average total yards per game is usually a little above 300. The graph reflects that, showing only a handful of games won below 300. Next is a heat map. In this graph, total yards is our x-axis and third down conversion is our y-axis. Each grid in the heat map shows the probability of a win relative to our two variables. The amount of blue is proportional to said probability. Both axes are using bins, which are the ranges of values. Again, using common sense, there's a low chance of winning if the Ravens have low total yards and a low third down conversion. If we look at the variables pulling all of the weight, we see our first taste of a 1.0 win probability at the 52% third down conversion and the 473 total yard bins. One big thing I need to emphasize is that a 1.0 win probability is not the same as a 100% guaranteed win. It simply means that all games with both of those metrics were wins. So in a way, it does give some predictive power, but it's still not wise to use 1.0 as a 100% chance of winning. Next, a calibration curve. A calibration curve simply illustrates how correct our model was in predicting a win versus actual wins. The straight dotted line is the ideal curve, which means the model was 100% in predicting all wins. The blue line with hard points is the model's predictions. We see the first point is at a 0.3 predicted win probability, but the actual win rate was a 0.4. So this means the model started off pessimistic. In the middle to upper ranges, it's pretty accurate, yet it gets a bit overconfident at the very top. Now on to marginal effects. While every other graph observes both variables, marginal effect graphs allows us to see how much a single variable contributes to the predictive probability. This is done by holding the other variables at its constant average. So if we want to observe third down efficiency's impact, we'll hold total yards at its average. Then we do the same for observing total yards, holding third down efficiency at its average. The line is just a predicted win probability. The shaded area is a 95% confidence interval, which just shows how certain these predicted win probabilities are. Notice they're most narrow towards the middle in both graphs, since that's where most of the data lies. The more data available, the more confident the prediction. Given the small sample size of 116 games across 7 seasons, this analysis can only be so precise. This is the nature of football, who doesn't play that many games. Compare that to basketball, where 116 games is about a season and a half. Or baseball, where that doesn't even crack a whole season. This histogram shows the frequency of our model's predicted win probabilities. It best illustrates the model's confidence throughout our data set. We see this graph tends towards higher probabilities, the highest being 0.8 for over 20 games. If 0.5 was the most frequent, that means the model had virtually no confidence. It's shrugging its shoulders and giving a random guess. The histogram is best compared with the calibration curve. The former measures the distribution of predictions, while the latter measures the quality of the predictions. This confusion matrix is my personal favorite visualization out of all the others. No percentages, no esoteric logos or advanced math needed to understand it. This is a simple 2x2 matrix that illustrates how many times the model was right and how often it was wrong. The x-axis is the model's win-loss predictions, and the y-axis are the actual results. The bottom 2 squares are all the actual wins, and the top 2 are the actual losses. The bottom left square means the model predicted a loss, which turned out to be a win, of which this happened 9 times. The bottom right square shows that out of the 116 games, the model correctly predicted a win 69 times, which is slightly above average accuracy. So whether the model predicted a win or a loss, if the result matches the prediction, that's a true prediction, meaning the model was correct. If it predicts win and the result was a win, that's a true positive. If it predicts a loss and the game was a loss, that's a true negative, which is healthily realistic. If it predicted a win but the result was a loss, that's a false positive, which means the model was too optimistic. If it predicted a loss but turned out to be a win, that's a false negative, meaning it was too doubtful. This matrix is tuned for a 0.5 threshold, meaning any predicted probability at or above 0.5 is considered a win. We could of course tune this to be higher, say at 0.6, and any prediction lower will be considered a loss. So, just using third down conversion rates and total offensive yards, we were able to build a statistical model that predicts the probability of the Ravens winning a game. Third down conversion rate emerged as a stronger predictor. The model's pseudo R-square of just about 0.12 shows the model is better than guessing, but still far from perfect. Again, football games within seasons are relatively spaced out compared to baseball and basketball, so given the small sample size, the data can only be so precise, especially when only using 2 predictors. I just kept it simple for my first end-to-end statistical analysis project.